This is day 5 of the CCNA course. Today we're covering IP addressing and the CCNA objectives 1.6, 1.7, 1.8, and 1.9. Let's begin. Alright, so what is an IP address? An IP, or Internet Protocol Address, is a unique identifier assigned to each device connected to a network that uses the Internet Protocol for communication. It serves two main functions: identification and location. So it uniquely identifies a device on a network, and it also provides the device's location within the network, allowing for proper routing of data packets. For the CCNA, you need to know IPv4 and IPv6, and in this video, we're going to cover these both deeply. We are going to begin with IPv4. IPv4 addresses are represented in decimal format, divided into 4 8-bit octets, and each octet is separated by a dot, a format known as dotted decimal notation. They range from 0.0.0.0 to 255.255.255.255, allowing for approximately 4.3 billion unique addresses. So this is your typical IPv4 address, and this is how it looks. It's broken down. So there are classes to IPv4 addresses. Originally, they were divided into 5 classes, which are A, B, C, and D, and E, based on their leading bits. Classes A, B, and C were used for general-purpose Unicast addressing, while classes D and E were reserved for multicast and experimental purposes. So, Class A, its range is 0.0.0.0 to 127.255.255.255. The leading bit is 0, and the default subnet mask is 255.0.0.0, or a /8 subnet mask. Class A addresses are used for very large networks. Class B ranges from 128.0.0.0 to 191.255.255.255. The leading bits are 10, and the default subnet mask is 255.255.0.0, or a /16. It's used for medium networks. Class C ranges from 192.0.0.0 to 223.255.255.255, and the leading bit is 110. The default subnet mask is 255.255.255.0, or a /24. It's used for small networks. Class D ranges from 224.0.0.0 to 239.255.255.255, and the leading bits is 1110. It's used for multicast. There is a Class E, but you'll never see it on the CCNA, and for that reason, we are not going to cover it more than just you knowing that it exists. There are certain ranges of IPv4 addresses that are reserved for specific purposes. There's the private IP addresses, or RFC 1918, which are not routable on the public internet and used within private networks. So they range from 10.0.0.0 to 10.255.255.255 and are Class A. Class B private addresses are 172.16.0.0 to 172.31.255.255, and Class C is 192.168.0.0 to 192.168.255.255. Loopback addresses range from 127.0.0 to 127.255.255.255, and it's used for testing and diagnostics on the local machine. More special IPv4 addresses are the link local addresses, or APIPA, through the maximum. And it is used for automatic private IP addressing when a device cannot obtain an IP address from a DHCP server. Broadcast addresses are used to send packets to all hosts on a network, and an example would be 255.255.255.255, which is a limited broadcast address. Now moving on to CIDR, or Classless Interdomain Routing. Knowing these 4 common prefixes and the subnet masks associated with them will make your life much easier when you're subnetting later. So there's the /8 prefix, where the notation looks like this, where it would be some range of bits, and then the /8. Subnet mask looks like this, and the amount of addresses the /8 prefix holds is that number. An example looks like this, and it's used for very large networks. Class A addresses use a /8 prefix. A /16 prefix has the notation of this and then /16. The subnet mask is 255.255.0.0 and it holds 65,536 addresses. An example can look like this, and it's used for medium-sized networks, and you'll see it with Class B addresses, which use the /16 prefix. There's the /24 prefix, where the notation looks like this, and then /24, and it has 255.255.255.0 as a subnet mask. It can host a number of 256 addresses, and an example looks like this, and it's used more for smaller networks, and Class C addresses use a /24 prefix. A /32 prefix would look like this, and the subnet mask is 255 all the way, and it can support one address, and it's used to specify a single host. This prefix length is often used in routing tables and access control lists. So what does it do? CIDR allows for more efficient IP address allocation by enabling subnetting and supernetting. Subnetting is dividing a larger network into smaller subnetworks, or subnets, and an example would be splitting 192.168.1.0/24 into multiple /28 subnets. Supernetting is the opposite, where it's combining multiple smaller networks into a larger network. For example, aggregating 192.168.0.0/24 and 192.168.1.0 into 192.168.0.0/23. So 224 networks turn into 23 networks. Benefits of it is efficient IP address allocation, because CIDR helps in reducing the wastage of IP addresses by allowing allocation in more granular blocks or smaller. It also brings improved routing, where CIDR reduces the size of routing tables by allowing route aggregation, which simplifies the routing process. And it's flexible, which means it supports networks of various sizes, making it adaptable to different networking needs. Example of CIDR usage would be, say you have this IP address. The prefix length is 24, which means the first 24 bits are in the network portion, which means the subnet mask looks like this, the network address is that, and the usable host addresses range from this to this, excluding the network address and broadcast address, of course, because you need those for the next address. If you further subnet this, you could get smaller subnets, which are /26. So each /26 network provides 64 IP addresses suitable for smaller segments within the network. So you're just breaking it down. Say there was like an office, you can have like one network for the janitors, one network for the engineers, one network for the doctors, something like that. In summary, CIDR enhances the flexibility and efficiency of IP address management and routing, allowing for better utilization of the finite IPv4 address space. So in brief, subnetting is done by borrowing bits from the host portion of the IP address to create additional network addresses. The subnet mask determines the division between the network and host portions. Example would look like this, where it indicates that the first 24 bits are network portion and the remaining 8 bits are for host addresses. So if you guys want to learn subnetting, a great source I'd recommend is Practical Networking, where he has a 7-part series where he covers everything about subnetting. This is how I learned for my CCNA, and I'm really recommending him. Now we're going to move on to how to configure IP addresses. It's fairly simple. You enable, you will get into global config mode, interface, and then set the IP address via this command. IP address, and then your network, and then the subnet mask. Then you just do a no shut, and that will assign your interface with the subnet mask and IP address. And that will assign that interface, that IP address, and subnet mask that you configured. That's all you need to configure an IPv4 address. We covered private addressing in the previous slides, but I want to explain why it's essential. It's essential because of many reasons, mainly in the context of efficient use of IP address space, network security, and ease of network management. There's many reasons on why it's important. Conservation of our public IP addresses is one of the biggest reasons. The IPv4 address space is limited with only about 4.3 billion unique addresses. Due to the rapid growth of the internet and the increasing number of devices, the available pool of public IPv4 addresses is nearly exhausted. Private IP addressing allows organizations to use a large number of IP addresses within their internal networks without consuming public IP addresses. This helps conserve the limited pool of IP addresses. It also helps provide enhanced network security, network address translation, internal network organization, and scalability and flexibility, avoiding IP conflicts and mergers and acquisitions, and cost efficiency. Common IPv4 address ranges are defined by the RFC 1918, and there are 3 ranges of IP addresses that you need to know, and you probably have an address in one of these ranges, which is allowing you to watch this video right now. Moving on to configuring IPv6 addresses. Configuring an IPv6 address is simple and easy, just like IPv4 addresses. You interface, then set the IPv6 address command, and plug in your address. Afterwards, make sure you configure IPv6 unicast routing so it can be routed over the network. To verify, use this command. Now let's quickly cover the different types of IPv6 addresses that exist. IPv6 addresses are classified into several types based on their intended uses. There's unicast addresses, anycast addresses, multicast addresses, and modified EUI-64 format addresses. Unicast IPv6 addresses are identifying a single network interface. There are 3 main types of IPv6 unicast addresses. There's the global unicast address, or GUA, and these addresses are globally unique and routable on the internet. There is ULA, or unique local addresses, which are used for local communication within a site or organization, and they are not routable on the global internet. And they range from FC00.7, and this is an example. Link local addresses. These are addresses used for communication within a single network segment, automatically configured on all IPv6 enabled interfaces. Look out for them by looking for this FE80. Anycast IPv6 addresses are assigned to multiple interfaces, typically belonging to different devices. Packets sent out to an Anycast address are routed to the nearest interface in terms of routing distance. There is no specific range, meaning any global unicast address can be configured as an Anycast address. Multicast addresses identify a group of interfaces typically belonging to different devices. Packets sent to a multicast address are delivered to all interfaces identified by that address. It would range from FF00, and this is an example. EUI-64 IPv6 addresses are used to automatically configure IPv6 addresses. It involves creating an interface identifier from the MAC address of a network interface. The process includes inserting FFFE in the middle of the MAC address and flipping the 7th bit. So this is how it would look like. There's the MAC address, and they'll just plug in the FFFE and flip the 7th bit. Configuring these addresses, you will just do the interface gigabit command, and then IPv6 address, and at the end of plugging in your IPv6 address, you write EUI-64. This will automatically generate the interface identifier using the modified EUI-64 format and append it to the network prefix. To confirm, use this command. So configuring IPv6 addresses and verifying them involves enabling IPv6 on network interfaces, assigning appropriate addresses, and using commands to verify the configuration. Understanding the different types of IPv6 addresses, which are unicast, anycast, and multicast, along with the EUI-64 format, is essential for effective IPv6 network management. Now we're going to move on to practice questions. What address is FE80./10? The answer is link local. Because I told you, remember to look out for the FE80 if you want to confirm if it's a link local address or not. What class address is 11.11.11.11? The answer is Class A. What prefix correlates with the 255.255.0.0 subnet mask? The answer is B/16. How many bits in an IPv4 address? The answer is 32. What type of address is this? The answer is A. Global Unicast. Thanks for watching. If you want to show your support for this series, please like, comment, and subscribe. This is Daud's Networking Labs, and I'll see you soon.